Hey folks, in this screencast we're going to expand on what we've already developed with angular momentum and create a more generalized form of this expression. And so what this means is that instead of being restricted to calculating the angular momentum of point P about an inertially fixed point like point O, shown here in this inertial reference frame, we're now going to relax the constraint of the point that we're calculating our momentum about, so we can use point Q. And point Q can be fixed in an inertial reference frame or it can be moving. So, to calculate the angular momentum about a moving point Q, let's first write the expression for the angular momentum. So it's the angular momentum of P with respect to Q as observed in an inertial reference frame. And this expression fortunately doesn't change. So this is R of P with respect to Q crossed with the mass of point P multiplied times the velocity of P with respect to Q as observed in an inertial reference frame. So when we have an opportunity, it's always a good idea to write our position and velocity vectors with respect to an inertially fixed point. So to do that, let's draw our position vectors. We have the position of Q with respect to O, and then the position of P with respect to O, and then the relative position between them, R of P with respect to Q. This is a vector triad that we're used to seeing, so we see that the position of P with respect to Q is equal to the position of P with respect to O minus the position of Q with respect to O. And then if we take the time derivative of this entire expression, as observed in the inertial reference frame, we get that the velocity of P with respect to Q, as observed in the inertial reference frame, is equal to the velocity of P with respect to O, as observed in the inertial reference frame, minus the velocity of Q with respect to O, as observed in the inertial reference frame. Let's substitute these two expressions into our equation for angular momentum, and we get that the angular momentum of P with respect to Q is equal to R of P with respect to O minus R of Q with respect to O plus the mass of our point P and then the velocity of P with respect to O as observed in the inertial reference frame minus the velocity of Q with respect to O as observed in the inertial reference frame. And so all we've done here is we've taken the expression that we knew before, and the expression itself hasn't changed. We haven't really made any different assumptions. We've just expanded its form, in which O is certainly an inertially fixed point, and then Q can be any point that's moving. So now if Q is an inertially fixed point, then what happens to this expression is that the velocity of Q with respect to O becomes 0, and we only have one velocity term, which would be velocity of P with respect to O, and then over here we just have the position vector as shown, and it looks just like our expression for the moment of momentum.